hybridization. All right, so we're doing hybridization. And when we're doing hybridization, we need to look at our sheet. So hopefully you've got your sheet near you while we're doing these hybridizations. So when we're doing this, I'm going to write this down here. So when we're doing these hybridizations, so you see how I've got two molecules or two numbers because there's two central atoms. So when you're doing your homework this week, you'll see there's some things that have two central atoms, but you see how I've like numbered them 1 and 2. So we're going to do the hybridization around each of these. And so when we do this, we call this our central atom. Here's B, 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 right? So that's going to be AB4, 4 electron groups. So carbon 1 has 4 electron groups. Carbon 2, if this is our A, here's B, B, B. So carbon 2 has 2 electron groups. Or sorry, 3 electron groups. I can count. 3 electron groups, right? So AB4, right? That's tetrahedral. AB3, trigonoplanar. So now we look at our sheet that you have. We look at our sheet, and remember, I don't have it on my PowerPoint right now, but if there's 4 things, you just go look, and then that 4 things means there's going to be 4 hybrid orbitals. So it's 1s, p, p, p. So it's going to be, this one's going to be sp3. This carbon has 3 electron groups, so that's going to be spp, sp2. You don't need to memorize the hybridizations. All you do is you need to remember the number of electron groups around the atom, because remember there's 1 s orbital, 3 p orbitals, and 5 d orbitals, right? It goes 1, 3, 5 that we learned from like a month ago when we were started with sp, ds, and f. So however many electron groups are, you just start counting. So if there's 2 electron groups, sp. There's 3 electron groups, spp, sp2. There's 4 electron groups, spp, sp3. So that's how you can figure out our hybridization. And so what does it look like, right? Remember, if we did our bonds, this is a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. One of these is a sigma bond, the other one is a pi, right? So this is this sigma bond. This pi bond, remember pi bonds are double bonds. That's this right here, this overlapping, that's the pi bond or our double bond, right? So it's kind of showing you the overlap, and this is what we did last time, showing the overlap of our hybridization. Okay, so let's try another one. So here's the Lewis structure. So I want you to take a minute and predict these hybridizations. Now there's a few hybridizations, right? There's a hybridization here, 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 right? So we have 1, 2, 3, 4 different things to look at. So I'm going to give you a second. I want you to predict the hybridization based on this Lewis structure. So try that, and then we're going to go over it in just a minute. All right, let's look at these hybridizations. So first of all, we know that hydrogen doesn't hybridize, right? And so again, when we look at these, we look at the number of electron groups. So let's just do, let me just erase these numbers so they're not in the way. So let's do boron. So we do boron, it's A, B, B, B. So boron is AB3, 3 electron groups. That's S, P, P, sp2. Now let's look at oxygen. Let's just do this oxygen. So here's our A, B, E, E, B. So that's A, and I know sometimes we use X's. I just use B's for bonded atoms. B2, E2. There's 4 total things, right? So when we go into our electron groups, there's 4 electron groups. Yes, it's A, B, E2 bent, but there's still 4 things attached to it. So that's S, P, 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 sp3, right? So you never need to memorize hybridization. All you need to know is electron groups. Now, if you look, all the oxygens are exactly the same. If we A, here's B, B, E, E, AB2, E2, 4 electron groups. We do this one, A, B, E, E, B, right? You get the point. I just did that one twice. 4 electron groups. So they're all sp3 hybridized. Okay, so let's try this one. So we only have one central atom here, it's nitrogen. And again, all we really care about is the number of things attached to hydrogen. So if this is A, there's 1 thing, 2 things, 3 things, A, B, 2, E. But again, that's 3 total things. So it's going to be S, P, P, sp2 hybridized. So if we look at the oxygen, so we only have 1 central atom, but if we look here just to see what does this oxygen have, this oxygen has a B and 2 E's. Again, that's 3 things. A B and 2 E's, there's no geometry because it's at the bottom, sp2. And if we wanted to just do this chlorine, again, the chlorine's not really bonded to anything, but we can still look at the number of electron groups around it. So here's our chlorine. There's an atom, an E, an E, and an E. That's 4 things, right? So it's S, P, 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 sp3 hybridized. Now, if we were going to, so if I asked you to draw this, which I very much might ask you to draw this on your exam, I might, not this exact one. So remember, these are sigma bonds. This is the pi bond, right? So you're going to have to identify sigma and pi. And so the sigma bonds are like an overlap, right? So they overlap. It's the pi bonds that look like the hot dog bun. So if you were going to try to draw these pi bonds on this, it would look like this. And then I just kind of like go like this and show the overlap. I just did it in a separate piece. So sigma bonds are in the plane, pi bonds are above or below the planes. Okay, so that's our hybridization. Now, this is what we did valence bond theory. But valence bond theory predicts properties better than Lewis. So remember Lewis structures, when we just started with the Lewis structures, but there was problems with the Lewis structures because it kept saying things had to be like 90 degrees. And so then we used hybridization to kind of better describe how, oh, it is. Okay, let me turn my video off. I'm plugged into the internet and everything. I'm turning my video off to hopefully help with the issue of the internet. Let me know if it gets better with my video off. Okay, sorry. I heard I'm kind of lagging. So let me know if it's still having issues or if it's better with the video off. Okay, so valence bond theory predicts better than Lewis theory. And it gives a better idea of our shapes of our molecules. And that's what we were doing with like AB4. It has, AB4 109.5, that's valence bond theory. But there's still problems with valence bond theory itself. So many properties of the molecules, valence bond theory doesn't do a great job with, and specifically the magnetic behavior of specific molecules. And also, valence bond theory presumes that the electrons are localized in orbitals around the atoms and not around the molecules themselves. So it's saying the orbitals are in between atoms. So you see how here with this one, we're saying, okay, this, yes, is a hybrid orbital, but it's only between these two atoms. What we're going to talk about is orbitals that are delocalized around the whole molecule. Is it getting better now that I turned my video off? By the way, is the lagging better? Yes, still kind of laggy. I'll try to talk slower. I know it's hard for me, but I will try to talk slower. Okay, and I have lots of written on these screens, so you should be able to read most of what I'm going to talk about. So we're going to talk about molecular orbital theory. So in molecular orbital theory, we're going to apply Schrodinger's wave equation. Remember when we learned about the N, L, M sub L, M sub S? That's Schrodinger, right? So he figured out a mathematical probability of where the electrons are going to be. And so we're going to use that to calculate molecular orbitals. Now, molecular orbitals are different than atomic orbitals. These orbitals are kind of delocalized around the whole molecule. So these molecular orbitals are estimated. And we start with good guesses and they're calculated. So you can't predict them necessarily. It's more of a computer model that has predicted them for us. And so they test them and tweak them. It's really made by a computer model. And so in molecular orbital theory, the electrons belong to the whole molecule. They don't belong to individual atoms. And we call this delocalization, meaning the electrons belong anywhere or to the whole molecule instead of an individual atom. And so we call this a linear combination of atomic orbitals, or LCAO. And again, these are made by using linear combinations. Nothing we found experimentally. We used a calculation and then made our best guess, did an experiment, and then altered the calculation. So these orbitals are wave functions. So remember when Schrodinger talked about how just like light can be particles or waves, electrons can also be particles or waves. And this has to do with the constructive and destructive interference of these wave functions. And I'm going to talk about what that means in just a second. So the molecular orbitals, so when the wave functions combine constructively, which means they come, think of it in the ocean, when waves kind of join together and make a bigger wave, that's a constructive wave, right? So we've all seen that. So when the wave functions combine constructively, they result in a molecular orbital that has less energy than the original atomic orbital. We call this a bonding molecular orbital. So you'll see we call it MO, right? Molecular orbital. And it can either be a sigma or a pi. And most of the electron density is in between the nuclei. And I'll show you a picture of this in just a second. When the wave functions combine destructively, okay, so you know when you go to the ocean and you have, it really happens when their waves are going back out and like, or sideways, and one hits the other and it kind of cancels them both out and makes them smaller. That's a destructive interference. So when the wave functions combine destructively, the resulting orbital has more energy than the original orbital, and we call it an anti-bonding molecular orbital. And this little star, that means anti-bonding. And most of the electron density is outside the nuclei. Okay, so remember when we've talked about electrons, low energy good, high energy bad, right? They always want to be in the lowest energy state. Remember, off bow, start low, go high. They always want to be in the lowest energy state. So keep that in mind. So bonding molecular orbitals have less energy, happy. Anti-bonding molecular orbitals, more energy. sad, right? They don't like more energy. So here's what they look like. So here is, we'll just say like hydrogen, right? And so it has one electron in each 1s orbital. So destructive interference, here's what we call it the sigma, like sigma star, sigma s orbital. This is the anti-bonding orbital. The constructive interference, you see how the overlap is right in the nuclei? This is a bonding molecular orbital. We just call it sigma 1s. So this one has less energy than these two combined. This one has more energy than these two combined. And again, I'm going to show you a picture of what I mean by the energy in just a second. So molecular orbital theory. So this is MO, those again, molecular orbitals. So electrons in bonding molecular orbitals are stabilizing, good, happy, lower energy. Electrons in anti-bonding, and remember anti-bonding are the stars, these are destabilizing, higher energy, bad, right? So they're higher in energy. The electron density is outside the nuclear axis, which isn't, we don't want to be outside, we want to be, it's stronger and lower energy in and at the nuclear axis. And these cancel out any stability gained in bonding orbitals. So again, anti-bonding, bad. Bonding, good. So here's what I mean with the energy. So here's a bonding orbital, right? Oh, sorry. Here's our orbitals right here. Here's our bonding orbitals. So if this is energy, do you see how, this should be a little bit higher. So here is the energy of a normal orbital. Here's our normal orbital energies. When we make these molecular orbitals, this bonding orbital, do you see how it's lower in energy than these? Happy. So our sigma 1s, happy orbital. Here again, here's our energy. Right here. Our anti-bonding orbital is higher energy, bad. Anti-bonding orbitals. Anti-bonding orbitals destabilize the molecule. Bonding orbitals stabilize the molecule. So how can we tell? And so we're going to use it to see, does an atom bond? Do two atoms, we only can do this two atoms, do two atoms bond, or they don't bond? Or is the bond stable or unstable? So we often use kind of a shortcut to figure this out, and it's called bond order. So bond order is just the difference between the number of electrons in bonding, happy orbitals, and anti-bonding, sad orbitals. We only look at the valence electrons. It can be a fraction. This is important, and you're going to use this in your Chem 101. So star this one. Higher bond orbitals means stronger and shorter bonds. Higher bond orbital, stronger bond, shorter bond. If a bond order is 0, then the bond is unstable compared to the individual atoms, and no bond will form, meaning the molecule will not occur. And then we're going to talk about this also, this paramagnetic and dimagnetic. So paramagnetic means it has unpaired electrons. Dimagnetic means paired. So remember this. It's kind of a hard one to remember. Paramagnetic, unpaired electrons. Right? So remember when we did like, if there's unpaired electrons, when we do our, remember this when we did like 1s, 2s, and then like, here's our 2p. So if this is nitrogen, it would have 3 unpaired electrons. That would be called paramagnetic, unpaired electrons. If all the electrons are paired, so this would be like neon, then it would be called dimagnetic. So I kind of remember this, it's kind of hard, but so di just means together, it means two, paired. That's how I think of it, like together paired. I have not found a good way to remember that paramagnetic is unpaired and diamagnetic is paired. If you can think of a great way to help people remember that, please let me know. Here's how we found our bond order. We take the number of bonding electrons in our happy bonds, in our happy molecular orbitals, and then the number of anti-bonding electrons in our unhappy orbitals. And then we divide it by 2. Okay, so let's look at what this looks like. Okay, so here's a 1s atomic orbital and a 1s atomic orbital. These are our new molecular orbitals. Sigma, happy, lower energy. Sigma star, unhappy, higher energy. This is a bonding orbital. This is an anti-bonding orbital. So because we have more electrons in the bonding orbital than there are bonding orbital in the anti-bonding orbital, this has a bond order of 1. So when we do this, so our bonding electrons are 2. See how we have 2 electrons here? Minus anti-bonding electrons, 0, divided by 2, our bond order is 1. This is a happy molecule. It will occur. And we know indeed hydrogen does bond. One hydrogen does bond to another because remember, it's the H in our Brinkelhoff. So here's what we look at with our orbitals. And here's our sigma orbital. So you see how, remember before we had like, if we had hybridization, I mean, hydrogen isn't hybridized, but if we just had like a sigma bond here, it would look like this. When we talk about these molecular orbitals here, we say it's the entire thing. So it's over the whole entire molecule. So let's do helium. Okay, so for our helium molecule, you can see, again, here's our atomic orbital, here's our atomic orbital, right? Each helium has 2 electrons, correct? So if we look at the periodic table, each helium has 2 electrons. They're in the 1s orbital, right? So we're saying, can we bond one He to another? So when we make these molecular orbitals, they split into our bonding orbital and our anti-bonding orbital. We follow the same rules with Hund's rule, right? And Pauli exclusion principle and Aufbau. All of those rules still apply. We're just applying it to molecular orbitals. So when we fill, see how there's 4 electrons here? So when we fill these, we go up, down, right? And then we move to the higher energy, up, down. So that's how we fill these. We fill them exactly the same as we filled them before. But now if we look at this bond order, there's 2 electrons in the bonding. There's 2 electrons in the anti-bonding, and we divide it by 2. Our bond order ends up being 0 divided by 2, which is 0. Our bond order is 0. This means this is an unstable molecule. It will not bond. And indeed, there is no He2 molecule. It does not exist, right? And so if it's 0, it means there's no net bonding interaction. So higher bond orbital, the higher the bond order, the stronger and the shorter the bond. If it's a 0, no go, not going to happen. Okay, now what about, so those are the s orbitals. So what about the p orbitals? So the p orbitals, so here's our hybridized p, well, these are our unhybridized p orbitals, right? So when we create these atomic orbitals into molecular orbitals, it kind of looks like a candy wrapper. That's our bonding. And see, happy, see how these are within the nuclei right here, like in between the nuclei? That's a happy bond. Happy. Do you see how these are delocalized, not in the nuclear plane? Unhappy bond. Here's anti-bonding, bonding. Here's what the 2 py's look like. See, again, these are going to be right near the nuclei. These are not. You don't need to know what these pictures are, by the way. I'm just showing you what they look like. Here's the 2 pz's. And again, you can see happy bonding, unhappy anti-bonding. Remember, anti-bonding always destabilizes our molecule. We like bonding orbitals. Okay, so since these molecular orbitals, we can't figure them out by looking at the periodic table. They're determined computationally, meaning a computer program determined them, and then we've tweaked them as the years go on. So the relative ordering of these molecular orbitals, again, is determined computationally. So there's no single order that works for all molecules. And so this is what the molecular orbitals look like for boron, carbon, and nitrogen. This is oxygen, fluorine, and neon. So again, low energy to high energy, we fill them just like we did before, right? Start low, go high. But if, for example, I ask you to do the electrons using molecular orbital theory for carbon, you're going to use this configuration. If I say, I don't know, for fluorine, you're going to use this configuration. You do not need to memorize these configurations, but when you are doing your Chem 101, you might need to refer back to this slide. These would be the only ones you do. And Chem 101 Chem 101 often gives you the picture. It says, here's what it is, because you don't need to memorize it. Because again, it's different for every molecule. And there's reasons beyond this, but we're not going to go into this. Okay, so let's look at why this molecular orbital theory seems to be better than the other theories we've talked about. Okay, so oxygen gas is paramagnetic. Again, what is paramagnetic? It means it has unpaired electrons. But if you remember when we drew our Lewis structure for oxygen, it does not have unpaired electrons. But using experimental, like here we're making oxygen, we have found that indeed experimentally, oxygen is attracted to a magnetic field. So unpaired electrons are attracted to a magnetic field. And so meaning that it must have unpaired electrons. But what we learned is all of oxygen molecules are paired. So neither Lewis theory nor valence bond theory, this is with our hybridizations, this is just our straight Lewis theory, neither of those predict that oxygen is paramagnetic. And so just as a review, remember diamagnetic means unpaired. So it's diamagnetic, it's not attracted to a magnetic field. Oxygen is paramagnetic, meaning it does have unpaired electrons. So valence bond theory and Lewis theory has kind of failed us here. So here's what we learned with our Lewis theory and our valence bond theory. Everything's paired, right? They're all paired up. So these guys are sharing a p orbital. They're hybridized, and these right, oxygen would be sp3 hybridized because there's 3 things around it. It shows they're paired, but they are not paired. So here's what oxygen looks like using molecular orbital theory. So again, valence bond theory says there's no unpaired electrons in oxygen. So it should be diamagnetic, which means it's not attracted to a magnetic field. But we know oxygen is paramagnetic, so it must have unpaired electrons. So that's why we're going to look at molecular orbital theory to see what does it mean by unpaired electrons. So if we look at our O2 molecule, okay, so oxygen has, right, here's our 2s orbitals. So let's just draw this what we're used to for, right? So for oxygen, it is 2s2, 2p4, right? Here's our 2s. Here's our 2p's, up, 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 down, right? So oxygen is just He, 2s2, 2p4, right? So we're just using what we know, and I'm just drawing this here and here. So here's our 2s's down here, and here's the 4s and the 2p's, because we have 2 oxygen molecules. We have 1 oxygen molecule here, 1 oxygen molecule here. When we put them together, that's our O2 for here's our molecular orbital theory. And again, you don't need to memorize this splitting at all. So when we fill these, we go from the bottom up using the same rules. So Aufbau says we start low, right? So if we look at our electrons, start low, and then we go high. We have to fill this before we go up. So there's our 2s's. So that's 4 electrons. So see how this is 2, 4, 2, 4. So there's 4. Now let's go to our P. We look at our P here. We have 8 because 4 plus 4 is 8. So we up, down, got to go to our next energy, right? Up, up, down, down, right? Because Hund's rule says the most stable arrangement is the one with the maximum parallel spins. So then we go up, up. There are those unpaired electrons, proving that oxygen, or verifying that oxygen is indeed paramagnetic. Oxygen O2 does have unpaired electrons. So if we look at this bonding orbital, we only use our valence here. So we look here. Let's erase these. We're just going to count the number of electrons. So in our bonding electrons, that's the ones without the star, we have 2, 4, 6, 8. 8 bonding electrons. Anti-bonding electrons. Those are the stars. Stars. We've got 2, 4. 4 anti-bonding. And remember with our bond order, so with our bond order, we take half the bonding minus the anti-bonding and then divide it by 2, which gives us a bond order of 2. So before I did it like this, I just divided this by 2, or you can multiply it by 1/2, right? It's the same thing. This makes my life a little easier. And so you can see there is a net bonding attraction because the bond order is greater than 0. So that's happy. So yes, O2 does exist as an atom. And because there are unpaired electrons, O2 is predicted to be paramagnetic. And indeed, oxygen is paramagnetic. Oh, here it is. So here's our bonding. So we had 8 minus 4 divided by 2, right? 8 minus 4 divided by 2, just to help you remember how we did it before. Or you can multiply it 1/2, same thing. Okay, so let's practice this. So this is showing that molecular orbital theory is superior in this case to both our valence bond theory, that was with hybridizations, and our Lewis theory, that was just our straight Lewis structures. Okay, so let's draw the molecular orbital diagram for N2 minus ion, and we're going to predict its bond order and if it's paramagnetic or magnetic. Okay, so first of all, N2. Again, we don't know what it's going to look like. So let me go back to this picture. This is why I said this picture is handy. So see, here's N2. So this is what it's going to look like. We're going to draw that. Well, not the whole thing. We're only going to do this because we don't need the whole thing. So again, we'll have a sigma 2s star, and then here's our splitting of our p orbitals. Okay. And again, you don't need to memorize that. I would give that to you just because that's a lot to memorize. So again, where did we get this? We got this because this is the linear combination for nitrogen. It's calculated. We can't predict it using the periodic table or any other method than a computer. And here's what the computer has said. Okay, so now we look. How many valence electrons are there in N2 minus? So 5 valence electrons times 2, right? And this again means plus 1. So there's 11 valence electrons. So we're going to put 11 electrons in our diagram. And remember, just like Aufbau says start low, go high, and we have to pair, right? And so this one's going to go up, up. Remember, that is Hund's law saying that we go up, up, meaning the most stable configuration is those with the most parallel spins. But then again, Aufbau says we have to fill this before we go up again. We're going from low energy to high energy. How many we used? 2, 4, 6, 8, 10, 11. right? And so when we do this, oh, here it is for you, all nice and pretty. So when we do this, we look at our bond order first. We can see there's going to be one unpaired electron, right? So let's look at our bond order. So we look at the number of number of electrons in our bonding. So we've got, that's a bonding. This is a bonding. This is a bonding. So we've got 2, 4, 6, 8. So we have 8 minus the number of electrons in our anti-bonding. Those are the stars, right? These are the destabilizing ones. Minus 3, and we divide that by 2, which gives us 5/2, right? So it was like 2.5, 2.5. Okay. So when we look at this, our bond order is 2.5. Now, and if we do this, this is going to be, we have an unpaired electron. So this is going to be paramagnetic. But what if we did it for N2? Just wondering. What if we did this for N2? So N2 has 10 valence electrons, right? So if this was N2, just want to do this first. This is N2. It has 10 valence electrons. This goes up, down, 2, 4, 6, right? 2, 4, 6, 8, 10. If we did our bond order for this, we have, right? 2, 4, 6, 8 minus 2 over 2, right? So that bond order is higher. That bond order is 3. So the bond order for the nitrogen molecule is 3, right? The bond order for the N2 minus molecule is 2.5. Because this bond order is lower than nitrogen, the bond should be weaker, right? The higher the bond order, the stronger the bond, right? The higher the bond order, the stronger the bond. Because this has an unpaired electron, this would be paramagnetic. If we go back to our nitrogen that I just did right here, which I must have deleted it. If we went back to our nitrogen, this was our nitrogen. Nitrogen would be dimagnetic because they're all paired. So you see the difference between paramagnetic has an unpaired electron. Dimagnetic, they're all paired. And again, paramagnetic is attracted to a magnet. Dimagnetic is not attracted to a magnet. Okay, so let's try C2 plus. So again, we'd go back to that picture for C, for carbon. I'm gonna have to go back to the picture. I don't have it memorized either. Here's our picture, carbon. Oh, same as nitrogen, yay. So it's carbon, so we would use this picture. Okay, so I'm just gonna redraw that picture. Too bad I just didn't copy this over. That would have made my life easier. Okay, so we've got sigma 2s, sigma 2s anti-bonding, and then we've got, and this is gonna be, oops, it's a little too close. Okay, well, won't let me, there we are. Pi, let's put this here. Pi 2p sigma 2p. I'm just copying the picture, by the way. Pi anti-bonding 2p sigma anti-bonding 2p. Well, you know, almost enough from there. So I just copied the picture over. Okay, so when we do this, we have carbon, right? So carbon has 4 valence electrons times 2, which is 8. And again, the plus means take 1 away. So we have a total of 7 valence electrons here. So when we're going to fill these, we're going to go just like off-bow, low to high. So 2, 4, 5, 6, 7. Okay, So we can see already, unpaired electron, this is paramagnetic, meaning it will be attracted to a magnet. It's unpaired electrons, right? We do our bond order. Remember, a bond order is going to be whatever's in the bonding, not starch. Here's these. So this is going to be five bonding electrons minus 2 anti-bonding electrons divided by 2, right? And so when we do this, we get 1.5. So 1.5, that would be our bond order for this one, and it would be paramagnetic. And so that's how we use, here's everything right here, nice and prettier. That's how we do our molecular orbital theory. And if you take 229, we're going to talk more about this also. Okay, so this is for atoms that are the same, but what about if atoms are different? We're not going to talk too much about this. So what about if they're different, heteronuclear versus homonuclear? So then when we combine these, so when we combine atomic orbitals that are equal energy, like carbon-carbon, nitrogen-nitrogen, oxygen-oxygen, they contribute to the molecular orbital equally. So it's easier to combine. But if we've got different atoms that have different energies, then our atomic orbital closest in energy to the molecular orbital contributes more to the molecular orbital. Okay, so what does that mean? It means it's not going to be so straightforward. So the more electronegative an atom is, the lower in energy its orbitals. So remember, lower energy better. So the lower energy atomic orbitals contribute more to the molecular orbitals. Remember, the atomic orbital is like 1s, 2s, 2p, 3s, 3p, that stuff. So the lower energy, so more electronegative, lower energy. Lower energy means contributes more. I don't want to write that whole thing. Contributes more to it. Higher energy atomic orbitals create antibonding molecular orbitals. Non-bonding molecular orbitals remain localized around the atoms. Like this means like the p orbitals, right? They're not the bonding nor the anti-bonding. Okay, so what does this mean? So here's NO, 2 different atoms. It means now not so same. It's not so much the same. So oxygen is more electronegative than, so we have here's our oxygen atom, right? So oxygen is 2s2 2p4. Here's our s2, here's our p4. Here's our nitrogen atom, right? 2s2 2p3. Here's our 2s, here's our p3. Right, so these are our atomic orbitals, which we learned before, okay? So oxygen is more electronegative than nitrogen. So its atomic orbitals are lower in energy than nitrogen's. Okay, so what does that mean here? So if we look here, again, here's our atomic orbitals. Oxygens are lower in energy, right? Here's a low energy, high energy. Oxygens are lower than nitrogens because it's more electronegative. So you can see here, look, oxygens are lower. Here's O, here's N. Oxygens are lower than nitrogen. When 2 different atoms combine, the lower energy atomic orbital makes a greater contribution to the antibonding molecular orbital. So the sigma S is closer to the oxygen's 2s than the nitrogen. And so you see how these kind of shift a little bit because of that. And so let's look at it with HF. And so F is super, so here's our atomic orbital F, and here's H. So F is so electronegative that all of its atomic orbitals are lower in energy than H's atomic orbitals, right? So here's F, here's H, lower energy. They're lower in energy. And in this case, like S2s orbitals are so low compared to hydrogens that it does not even contribute to the molecular orbitals. See, there is S isn't even in here. So the molecular orbitals of HF, they're approximated by the linear combination of the 2px or 2px or 2py and the 1s. The other 2p orbitals remain localized on the F atom, and they appear in our non-bonding orbitals. So basically, what does it mean? Do you see how these molecular orbitals here, they're closer to this one because this one is so electronegative. This one is up here above this. This is our destabilizing electron orbital, our molecular orbital. So that's just a little bit about electronegativity. So again, the more electronegative it is, the lower the energy is, and the lower the energy, it contributes more to our bonding molecular orbitals. Okay, so that's all we have for this section. So we have completed this piece of our module. Any questions on molecular orbital theory before we go on? Okay, so we're going to just take a little bit of time to introduce intermolecular forces. All right, so if you remember, everything that we've been doing so far has been to figure out why atoms act the way they do, or why molecules behave the way they do, right? That's what we've been trying to figure out this entire time. Why do molecules behave the way they do? I'm going to try turning on my video just for a second. We'll see what happens. I'm keeping an eye on my task manager to see if it goes crazy. Okay. This is intermolecular forces. So remember we learned, okay, where are the protons, or what's the nucleus? Remember all of that, all the way back to like Rutherford's gold foil and crazy Thomson and his plum pudding. And then we figured out, oh, Bohr said, oh, they're around the nucleus, like planets orbit the sun. That's where the electrons are. And then Schrodinger's like, no, they're not. And then we learned about our N, L, M sub L, M sub S. And we're like, there's where the electrons are. They're in orbitals, these three-dimensional areas that are wacky looking all around the atom. That's where the electrons are. And then we use that. And then from that, we figured out the valence electrons, right? That's when we learned 1s2, 2s2, and the valence electrons. Those are the outermost electrons. And then we figured out, oh, those outermost electrons, those are the important electrons. Those are the ones that are involved in bonding. And then we learned about atomic and ionic bonding and sharing of electrons or transferring of electrons, right? And then from there, we got to Lewis theory, and we're like, because of where these valence electrons are located in an atom, this is why atoms or molecules bond the way they do, either ionic or covalent. Based on the way they bond, that's how we can figure out their shape, right? That's how we can figure out the shapes of the atoms, right? And that's kind of where we are right now. And then based on the shapes, we can figure out if the molecules are either polar or non-polar, right? So that's kind of where we've ended, kind of, and then we talked about a little bit more about theory. So we went through this whole thing all the way to get to this, intermolecular forces. Why are some molecules or substances liquids? Why are there gases? Why do some things boil at 10 degrees Celsius? Why do some things boil at 100 degrees Celsius or 1,000 degrees Celsius? It all has to do with their intermolecular forces. So these intermolecular forces, so we know that opposites attract, right? We talked about Coulomb's law, right? Opposite charges attract to each other by electrostatic forces. The strength of these intermolecular forces varies. Some are small, some are large. And it depends on the kind of particles, and the stronger the particles are, the tighter they are to each other, meaning the less movement that they have. So first, we're going to talk about the kinetic molecular theory of gases. So again, we're going to look at how these particles move. So the kinetic energy is so large that it overcomes the attraction between the particles. This means the material must be a gas. So just to review how things move. Solids, all they can do is vibrate, right? They're fixed. They can't move. They're fixed. Liquids, right? They can vibrate, they can rotate. Okay, they can kind of translate, right? They can kind of move. But gases, they're free. They can go wherever they want, however they want, anywhere they want, right? So they have their kinetic energy, the energy of the molecules is very high. So, right, if you have to go from this to this, you absorb energy. So gases have a lot of energy so they can move. In an ideal gas, which we're going to be talking about through our lab the next few weeks, the particles have complete freedom of motion, especially translational. Translational means they can go anywhere they want to. This allows gas particles to expand to fill their container. And we already know this, right? Think about, remember when you were in a classroom and somebody would put lotion on their hands, right? And then the whole room would smell like that? Or ever driven by a skunk and you see the skunk and you know your car is going to smell like skunk. Gases completely fill their container, right? They can flow. This also leads to the fact that there's large spaces between the particles. So for example, in the room you're in right now, if you have a coffee cup, you could take all the gases in the room you're in right now, and you could compress them into your coffee cup because there's large spaces between the containers. They have very low densities and they're very compressible. So when we look at these phase changes, again, solids can't really move, right? Liquids, they can move a little bit more, right? Liquids, they can move. Gases have complete freedom. So we're increasing, when we heat this up, we're adding energy, and then we get more movement. We go here, we're adding more energy, and we get more movement. Vice versa, if we go from a gas to a liquid, we're removing energy, right? Because gases are going like this. To slow down, they have to give off energy. Liquids to solids, again, if you're moving like this, then now you're only going like this, you have to give off energy. So that brings us to intermolecular attractions. So the strength of attraction between particles of a substance determine its state, meaning is it a solid, is it a liquid, or is it a gas? At room temperature, moderate to strong attractive forces result in the materials being either solids or liquids. The stronger the attractions, the higher the boiling points of the liquid and the higher the melting point of the solid. So the stronger attractive forces, and we're going to talk a bunch about these attractive forces. So why are molecules attracted to each other? So remember Coulomb's law? Opposites attract, right? Again, you don't need to know the math of this. You just need to remember that this is based on, this is charge. So this is like a positive one or a negative one or a negative two. And this is distance. How far they are each other. So intermolecular attractions are due to the attractive forces between opposite charges. Remember when we talked about polarity? Remember there's a positive end and a negative end? Those are our positive and negative forces. Even nonpolar molecules, we're going to find out, actually have attractive forces. So if we look at water, so here's our water molecule. Remember, the O is a little bit negative, and the H's are a little bit positive. Remember, if we drew a dipole here, we would draw it like this. That's us drawing our dipole. Same here, here's our oxygen, which is a little bit negative. Here's our hydrogens, which are a little bit positive. If we drew our dipole here, it would look like this. This attraction between this side that's positive to this negative, this attraction this is what we call an intermolecular force. It's a force that the positive to the negative end of a molecule are being attracted to each other. Opposites attract. So polar molecules are attracted to each other because the positive ends are attracted to the negative ends. Now, these intermolecular forces are between molecules. They are not bonds. This is a bond between an O and an H. That is a covalent bond. This is just an intermolecular force. Intermolecular forces are much weaker than bonds. So I'm going to talk about strong and weak intermolecular forces, but they do not compare to bonds. Bonds 10 times stronger than an intermolecular force. So the larger the charge, the stronger the attraction. The longer the distance, the weaker attraction. So these attractive forces, again, are very strong compared to bonding forces. Very strong. So the larger the charge, so the more, go back to my red, the bigger the dipole, the stronger the charge, the stronger the attraction, right? The longer the distance, the weaker attraction. So the bigger they are, the weaker they're going to be attracted. So we're going to talk about these. So trends in the strength of our intermolecular forces. So again, the stronger the attractions between either the atoms or the molecules, the more energy it takes to separate them. When we boil a liquid, what we're doing is we're adding enough energy to overcome the attractions that are holding the molecules together. So with water, right, we have, which I can't draw, let's remember this. I should probably do this with the O's and the H's so you remember. So with water, remember, if we had to draw, this is a little bit positive. This is a little bit negative. So this is what we call an intermolecular force, the positive being attracted to negative. So the stronger the attraction between the positive and the negative, the more energy it takes to separate them. So when we boil a liquid, what we're doing is we are, breaking those intermolecular forces, right? These intermolecular forces are holding these two molecules together. But when we add energy, we break them. So when we boil a liquid, we have to add enough energy to overcome this attraction between the particles. Now, again, we're just breaking the attraction between the particles. We're not breaking the bond. Right? Again, we're not breaking ionic or covalent bonds, right? Those are sharing and transferring electrons. Those are strong. We're just breaking these little forces here that hold the molecules together. The higher the boiling point, the stronger this attraction is. The stronger the attraction is, the more energy we need to break it. So the higher the boiling point, the harder it is to break these forces up. Okay, so the different kinds of intermolecular forces. So we have dispersion forces. These are very weak. We've got dipole forces. These are stronger. And then we have the strongest, which are hydrogen bonds. So we're going to talk about each of these. So dispersion forces, these are just temporary dipoles. It means they're polar for a moment, for like a nanosecond. Dipole is kind of exactly what it sounds like. Remember, our dipoles are the things with the arrows? It's this, right? It's a dipole being attracted to a dipole. And so these are polar molecules, right? Since polar molecules have dipoles, that means dipole-dipole attractions are attractions between two polar molecules. Now, hydrogen bonding is just super strong dipole-dipole. It just means they're superpolar molecules. And these we're going to talk about, these are just, there's only a few molecules that can do this, but again, super strong They're just super strong dipole-dipole forces. So again, these are just superpolar molecules. We call them superpolar molecules. So these are our three forces that hold our molecules together. All right, so let's look at our weakest force. So our weakest force is called dispersion forces. So these dispersion forces are due to the electrons in the molecule, okay? So can we all agree that all molecules have electrons? Yes, right? All molecules have electrons, right? Yes, they do. So what happens in a dispersion force, mind you, I can't draw, is this is a molecule and this is a molecule. And both these molecules have electrons, right? These are electrons. Right? And the electrons are hanging all around the molecule. When this molecule gets close to this molecule, right? Coulomb's law, like charges repel, the electrons are going to repel each other. So what happens, draw this a little smaller, is the electrons are going to repel each other. So the electrons, whoops, the electrons are going to move from one side to the other side. Well, when the electrons move to one side, that leaves the other side just the littlest bit positive. And the other molecule goes, oh, positive charge. And guess what happens? All the electrons are like, oh, I like positive charges. And they line up and then they leave the other side positive. This lining up of this negative and sort of positive, sort of negative charge, this is what happens in a dispersion force. So the region with excess electron density, really should have drawn this a little better. These are negatives. The region with excess electron density here has a partial negative charge, and it is the babiest bit of a negative charge. The part that has a depleted electron density has the babiest positive charge. This is temporary. Why? Because electrons move very, very fast, right? So this literally like happens and it's gone, and then it happens and it's gone, just like that, because electrons move very fast. So this lining up and this, what ends up being this attraction here between these molecules lasts like a nanosecond, and then the electrons go right back to this, and then they get close to each other again and then do this, and then the electrons move again. And so it's this very instantaneous positive and negative, partial positive and negative. It's a temporary dipole, a temporary positive, a temporary negative that lasts like a nanosecond, right? This is what we call a dispersion force. It's also called London forces. It's also called London dispersion forces. Often we'll call them LDFs for short, for London dispersion forces. They've got a couple different names. So who has these London dispersion forces or these dispersion forces? Everybody's got them. Why does everyone have them? Because every molecule has electrons. So if a molecule has electrons, which all molecules have electrons, that means all molecules have dispersion forces, or LDFs, London dispersion forces. Because Fritz London, he's the guy that discovered these, so that's why we named them London dispersion forces, because Fritz figured them out. So these are temporary dipoles in one molecule, and it induces a dipole in the surrounding molecules, right? So when the electrons line up over here, it leaves a little bit positive here, and then the molecule's like, hey, look at that. We're going to be attracted to those positives. Let's line up all of our electrons so we can have this induced dipole. It means it induces the dipole. So here's me. This is a little bit better of a picture. So here's our electrons chilling out around our nucleus, right? They're just here and here. Well, by chance, sometimes, here we are, they're moving around, and then they're lining up, right? They're both on the same side of the molecule. When this happens, this part of the molecule ends up having a little bit of a negative charge, and this part ends up being a little bit positive. But again, this lasts like a nanosecond, and then it's right back to these two, right? So in a nanosecond. But when this happens, if another molecule or atom is close enough, it's like, oh, I see your negative charge. And it's like, so if this lines up here, negative on this side, ends up being a little bit positive. This is our molecule that lined up. Then this molecule is like, I see a positive charge. Its electrons now line up over here. That is our dispersion force. And the same thing happens here. So when this one lines up, it leaves this side without electrons. So it's a little bit positive. And this molecule is like, hey, we see the positive. The electrons now line up. So they're a little bit negative. And again, there's our dispersion force. But remember, electrons move ridiculously fast. So these last like nanoseconds. So they are not strong. So sometimes we call these like instantaneous dipoles or induced dipoles, temporary dipoles. A dipole, remember, just means one side's a little bit negative and the other side's a little bit positive. But these are not permanent dipoles. They are temporary. They last for a nanosecond and then they're gone. So dispersion forces are very weak. Weak meaning super, super, super easy to break because they only last for a nanosecond. So again, we call these induced dipoles, and they're caused by electrons on one molecule distorting the electron cloud on another. So here's my try and an animation of this. Okay, so here's two molecules. You see how they have negative charges? Those are the electrons, and the electrons are zooming around. And then this one's like, oh, gets close. And the positives now all of a sudden line up. And that is our induced dipole. So now this side's a little negative, this side's a little positive, this side's a little negative, this side's a little positive, and it's this attraction between the positive and negative, which lasts like a second, right? So who has London dispersion forces? Everybody. But they're very, very weak. They're very, very temporary. And the bigger the molecule is, the stronger the London dispersion force is. Now, why? Well, the bigger the molecule, the more electrons it has. The more electrons it has, the more electrons are lining up, which means the more positives are lining up. Bigger positive, bigger negative, stronger attraction between the two. Larger molecules, more electrons. More electrons, stronger or bigger positives, bigger negatives. So again, the size of this induced dipole, the magnitude or the size depends on the polarizability or how big it is. So the bigger the molar mass, the more electrons there are. The more electrons there are, the bigger the electron cloud, which means it's more polarizable, which we can line up more of them, which means the attractions are stronger, which just pretty much means bigger molecule, bigger LDFs. The shape also determines the London dispersion forces. Now remember, every molecule has these London dispersion forces. Everybody's got them. So the shape also determines. So if you have a flatter shaped molecule like this versus, so here's our larger, flatter molecule versus a molecule that's got not so much interaction. So a molecule that looks like this versus this has less ability to interact, right? So if there's more surface to surface contact, see how there's more ability for this interaction to occur? It's a flatter molecule. More surface to surface contact means larger induced dipole, stronger attraction, right? So if it's flat, there's more interaction than if it's a circle. Okay, so we're going to keep going on with these London dispersions, but we're going to go into this next week, right?